Continuing our study of closed sets, in this lecture, we're going to talk about the closure of a set in a metric space. So let's go through this one sentence definition. The closure of some set we'll call A is defined as the intersection of all closed sets containing A. Take a moment to reread this sentence, and I want you to come up with one observation, maybe more, about the closure of A as a set in its own right. All right, here's something you may have realized. The closure is going to produce a subset of the metric space, and it's being defined as an intersection of closed sets. So that might ring a bell. In an earlier video, we proved that any intersection of closed sets is closed. So the closure of A is a closed set. So this implies that the closure of A is closed. All right, let's make a few other observations. It's an intersection of sets which contain A. So what that means is that A belongs to every set in this intersection. So A will belong to the closure of A. This might seem obvious, right? But we want to make sure that things we want to say are true are actually true from the definition. So maybe I'll write it here. A is a subset of the closure of A. All right. What if A were closed itself? If A is a closed set, and we're taking the intersection of all closed sets containing A, basically, I would imagine like kind of whittling down to just A itself. So if A is closed, it must be its own closure. So in general, it's a subset, but let me add to this that A equals its own closure if and only if A is closed. That just falls right out of this definition. I feel like there was something else I wanted to say. Oh yeah, and along with this, how I like to think of the closure is it's the smallest closed set containing A. And to establish that out loud, imagine I say the closure of A is the smallest closed set which contains A. If you proposed a smaller closed set containing A, that would go into this intersecting process, which would mean that either we were having the same set or my closure of A was incorrect, right? So if I add a smaller set or I include a smaller set into this intersection, we're just going to narrow the intersection down to that smaller set. So the closure of A is the smallest closed set containing A. When A itself is closed, it must be A. I like to think of the closure of A as taking a set, which is possibly not closed, and kind of closing it off the most natural way possible. So most natural way possible will come up in a theorem that we'll prove in a minute. But before we get there, let's use this definition on these two examples. So the first one, we want to consider this Archimedean set of, it's a subset of R, and the members of the set look like numbers of the form 1 over n. So 1, a half, a third, a fourth, a fifth. We've looked at this set a couple of times. I'm going to give you a systematic way to show what the closure of this set must be in a moment, but take a minute, just experiment with this. What do you think the answer should be? This can be a difficult computation to perform with just the definition because you might be trying to imagine every possible closed set that contains the Archimedean set. Here are some examples. The whole real line is a closed set which contains A. The closed interval from -10 to 10 contains A. The closed interval from 0 to 1 contains A. Right, so it's a bit of an unspecified notion, this idea of trying to take every possible closed set containing this particular subset of R and compute the intersection. So if I'm just going to use this definition, I want to come up with a family of closed sets containing the Archimedean set whose intersection I understand, but which convinces me that I have indeed computed the closure of A. All right, so here's my strategy. I'm going to define a family, A sub n, to be 0 to 1 over n, union everything that's not included in this closed interval, but which belongs to the Archimedean set. So if this is 0 to a third, I would be leaving out a fourth. Sorry, I would be leaving out 1 and a half. Okay, I think I did that right. So 0 to a third. It's like, what do I not cover with this closed set? I wouldn't cover 1/2 and 1. So that should be phrased as 1 over n minus 1 all the way through 1. Okay, since I didn't say that very well, let me write down the first few. A sub 1 will just be the closed interval from 0 to 1. Okay, that's a closed set containing the Archimedean set. A sub 2 will be the closed interval from 0 to 1/2, together with the isolated point out at 1. My marker is a little bit squeaky. A sub 3 will be 0 to 1/3, union two isolated points at 1/2 and 1. A sub 4 will be 0 to 1/4, together with 3 isolated points, 1/3, 1/2, 1. Should be clear that these are all closed sets. They consist of a closed interval together with a finite number of isolated points. So this is a union of a finite number of closed sets. That's going to be a closed set itself. If you haven't already reached an answer you feel certain about, take a moment to compute the intersection of this family for all natural numbers little n. To compute the intersection, we need to figure out all of the real numbers which belong to every member of this family of closed sets. By construction, the Archimedean set belongs to every A sub n, which is necessary for us to be computing the closure. Right, so this is going to include all members of the Archimedean set between 0 and 1 over n. Sorry, not 0, but between 0 and 1 over n, and then the rest of them. So every member of A belongs to each A sub n. No other positive numbers will belong to the intersection when I look at all of these because of this narrowing process happening with this first closed interval. So if I have a number of the form 1 over 50, and then 1 over n slides to the left of that, that's okay. 1 over 50 will be placed over here. But if I have something like 1 over 50 pi, which doesn't belong to the Archimedean set, eventually that will be removed from this closed interval, and it won't be placed over here. So the only positive numbers which live in every member of this family of closed set are the Archimedean set values. So that's good. No negative numbers, but also 0. So notice by design, 0 is in every single member of this family. So this is not every closed set which contains the Archimedean set, but look what we have. We have an intersection, which is the Archimedean set plus one single point. We're not going to find a smaller closed set containing the Archimedean set. Okay, so let's say the closure of A is A itself together with the singleton 0. Just to reiterate, each of these is closed. This infinite intersection is closed because any kind of intersection of closed sets is closed. We've taken a set which was not closed, and we've included one single point to close it off. So this is a closed set, and it's got to be the smallest closed set containing A. All right, so that was our first example. The second one's much easier. I just threw it on here because I have room. What about in a discrete metric space? In a discrete metric space, every set is closed. So by this observation, every set must be its own closure. So not too much to say, and we won't look at more examples of closures in discrete metric spaces because it's kind of a silly question. Every set is closed. Returning to our first example, when we talked about accumulation points, we said that the accumulation point, the only accumulation point for the Archimedean set is 0. And here we're saying the closure is the original set together with a missing accumulation point, an accumulation point that didn't belong to the original set. Turns out that is an illustration of our next result, which will give us another way to compute closures, which might be easier to use in practice than this definition in terms of intersections. A moment ago, when we computed the closure of the Archimedean set, I pointed out that it was the union of that set together with the single point 0, which is in fact its only accumulation point. That's a nice example of this theorem, which tells us that the closure of A can be found if you can take the union of A and its family of accumulation points, which I will denote capital L, where capital L here is secretly standing for limit point, just another word for accumulation point. All right. Sometimes this is easier than that notion of an intersection of every possible closed set containing the original set. So if you can look at a set and figure out what its accumulation points are, you just take the union of that set and its accumulation points and boom, you've got the closure. So for the Archimedean set, we could have done that a lot faster than the method we took, where we wrote down that family of closed sets. I'm going to prove this for you, but I'm going to do something kind of funny, where this is a perfectly nice set equality, but instead of working with this, I'm going to essentially take the complement of both sides and say that this statement is equivalent to saying that the closure of A complement is the complement of this union. By De Morgan's law, that's the intersection of their individual complements. So this is equivalent to the closure of A complement is A complement intersect L complement. This is not at all required. So if you want to prove this, go ahead. I like this approach because the closure of A complement has a really nice property that I just particularly enjoy working with. So just take a moment and figure out one word, one adjective that applies to the closure of A complement. The adjective I was looking for was open. So the closure of A we know is closed, therefore its complement must be open. I like open sets because it gives you like this notion of a neighborhood to work with, so I will employ that tactic. Another thing to observe about the closure of A complement is that it does not contain any point from A, because A is a subset of the closure of A. So if I'm looking at the complement, I know nothing in the complement belongs to A. This is a set equality proof, and you might be able to show like reverse containment at the same time. I don't have this proof written down here. I'm just going to make this up as I'm doing it. So I will do a traditional left-hand side as a subset of the right-hand side and right-hand side as a subset of the left-hand side. So it's like an if and only if kind of dual direction proof. So we will do both directions. Before I do that though, let me just write down the observations that I just stated out loud. So notice that the closure of A complement is open. And since A is a subset of the closure of A, the closure of A complement contains nothing from A. So we can write the closure of A complement intersect A is empty. Okay, let's show that the left-hand side, this set, is contained in the right-hand side. Again, there might be a faster, more direct way to prove this, but whenever you're trying to show two sets are equal, it's always a valid approach to show that an element from the left must be an element in the right and vice versa. So to do that, let me say, suppose X is in this closure of A complement. Then I know that X cannot be in A, which immediately places X in A complement. Moreover, X is an interior point because this is an open set. So around X, I can find a neighborhood that stays entirely inside of this set, which means it can't pick up any points from A, which means it can't be a limit point, which means X cannot be a limit point, or sorry, an accumulation point of A. Mixing up my words here. But the idea is, again, that we can form a neighborhood around X that stays entirely in this set, and that's going to tell us that X cannot be an accumulation point of A. Moreover, since there exists an open set U, sorry if I'm writing small, but there exists an open set U so that X is in U, and that stays inside of the closure of A complement. In other words, U intersect A is empty. Definition of an accumulation point is every open set around X should be able to scoop up something from A. That's not happening here. Thus, X is not an accumulation point, which puts it in LC, the complement of the set of accumulation points. All right, we've got X in the complement of A. X is not an accumulation point, so X is in this intersection. It belongs to both. I wrote that out in full detail, but this really could be a one-line statement. So, if you pass immediately from this, you figure out X is not an A and it can't be an accumulation point of A. Let's go the other direction. Suppose that Y is not in A and it's not an accumulation point of A. It's going to be this in reverse. Since it's not an accumulation point of A, there's an open neighborhood around Y which does not pick up any points from A, and since Y is also not in A, the entire neighborhood does not overlap with A. So then, I really should write out this whole phrase here, but because I'm working on a board, I'm just going to abbreviate. There exists open U. I really don't like that, in formal writing, but I don't want to run out of room here. So then there exists an open set U, just like this, so that, let me first write out our terminology that looks like an accumulation point. So, so that U take away Y intersect A is empty. This is what it means to say that Y is not an accumulation point of the set A. I can find a neighborhood around it, which, kind of ignoring Y for the moment, contains no point from A, scoops up nothing from A. But Y itself is also not in A. So since Y is also not in A, I might as well just say that U intersect A is empty. Or in other words, U is contained in A complement. Let me pause the writing just to sketch a picture. Suppose that this is A. What we've done is grabbed a point Y, which is not in A, and it's also not an accumulation point of A. So I imagine it as having some kind of distance away from A. Might as well put it over here. It's just not close to A. Since it's kind of separated from A, it's not in A, it's not close enough to be an accumulation point of A, we can find this neighborhood U, an open neighborhood around it, which has no overlap with A. Okay, that's where we are here. Now I want to point out that if U is contained in A complement, so out here, that means that A is contained in U complement. So that should be pretty clear from the picture, but I wanted to draw that before writing it down because I'm basically going to reverse the roles of the sets here. So if I take U complement, that's where A lives. Thus, A is contained in U complement, which is closed because U is open. That's good because an intersection is a subset of every member of the intersection. U complement is now a closed set containing A. So the closure of A will be a subset of U complement. So let me just draw an arrow here. Thus, the closure of A is a subset of U complement. So the closure of A lives in the complement of U, which means that nothing from U, including Y, can be in the closure of A. Thus, Y is in the closure of A complement, which is exactly what we wanted. Okay, when you're doing these kinds of proofs, it can be helpful to sketch a picture. A picture is not a proof, but sometimes it helps you realize, like, oh, look, I have U kind of over here. U complement is where A lives. So I thought that was a nice chance to pause and kind of sketch out what this argument is. Speaking of this argument, some of these phrases could probably be condensed. For example, here I kind of wrote out a lot to say that U is in the complement of A. It also might be preferable to work with the statement as it was given instead of doing this like alternative approach. The reason why I wanted to do this, just kind of looking at the statement, I thought, I don't know what A looks like. I don't know what L looks like. So I'm not really sure how to take their union, but I like working with open sets. And the reason why is in an open set, every point is the same kind of point. So in an open set, every point is an interior point. You can always sketch neighborhoods around points in open sets and know, like you can always find a neighborhood that stays inside of the open set. That gives you a lot of power. So that's what I was calling upon here. Whereas in sets which are not open, like I'm getting a little bit off topic here, but let me just compare an open interval to a closed interval. Sorry, that's supposed to look closed. In this situation, every point is an interior point. In this situation, I have interior points, but I also have points which are not interior points. So I like the consistency of open sets. That's why I passed into this set instead, because this is an open set, and I just like to work with that. Okay, we are almost done with this lesson. What I want to do now is a few more examples of taking sets and computing their closures, but this time we're going to work with this characterization, and it's much faster than how we started. Sticking with the theme of the last theorem, let's see if we can compute these closures pretty quickly, because I think for all of these, we can look at them and eyeball what the missing accumulation points are, so what we need to include in order to close off each of these sets. For each one, A is the set itself. Let me identify the accumulation points. For the set of rationals, I believe we showed that the set of accumulation points is the whole real line. So the closure of the set of rationals is the union of the rationals and R, but that's just going to be R. For the second one, the open interval from 0 to 1, if I said, hey, close that off, you would tell me the closed interval from 0 to 1, right? But here we can say the set of accumulation points for the open interval is the closed interval. Be careful not to say just 0 and 1. Sometimes students, when I ask them for the accumulation points for a set like this, they give me the interesting ones, which are at 0 and 1, but really the whole interval from 0 to 1 is a family of accumulation points for this set. Okay, all that to say, the closure of the open interval from 0 to 1 is indeed the closed interval from 0 to 1, as you may have expected. The next two examples are in R2. I think I'll just sketch pictures. So for this one, we have all of the pairings x and y so that the product is positive. So in other words, the first quadrant and the third quadrant. Not the axes, but if I take any point on the x or y axes and draw a neighborhood, you're going to scoop up something from either the first quadrant or the third quadrant. So for these two from the first quadrant, for these two from the third quadrant. So it's going to be the set of points x, y, so that the product is greater than or equal to 0. Like that. So that's the closure of this set. For the last one, this example is really not that interesting. It's the open disk. And for some reason, I added to that the point at 1, 0. So we have the open unit disk. And also, for some reason in the set, we have this point. Close this off means give me the solid closed disk of radius 1. Okay, so I hope these 4 exercises show you, in case you needed extra convincing, that that theorem we just proved was very useful. Thank you for your attention.